Welcome to the DVFS plugin video. In this video we show two small demonstrations on how to set the energy consumption and total cost of ownership as tuning objectives. The DVFS plugin features multiple tuning objectives which are configurable through environment variables. There are three main models used, one for energy, one for power, and one for time. All of the tuning objectives rely on a main model or a derived model. The export variable for the model which corresponds to the same tuning objective must be set before launching the application in the same terminal. There are several tuning objectives additional to the energy consumption. For instance, there is the energy delay product, power capping, total cost of ownership, and other policies like energy consumption for an allowed performance degradation. Of course, the choice of the metric depends on the needs of the user. We will show a demo for tuning the energy consumption as well as the total cost of ownership. It is recommended to use the energy consumption metric when other costs related to the time are minimal compared to energy costs. It can be configured by exporting the variable shown here, and it takes either the value 1 or 2. The only difference is that in the first case the energy is modeled directly. In the second case, power and time are modeled separately and multiplied. The tuning objective for energy consumption can thus be used with the two previous models. The tune code is SAISO, which is an application that simulates seismic waves and earthquakes. The code has been instrumented with 3 regions, one in the main loop, and 2 nested regions within a routine as shown on this slide. We are now connected to SuperMOOC and we have previously set up the load leveler script. We defined the environment variable for the model equals to 2 and notice that we identified the output of the job with the keyword energy. We are running the SAISO application. Once we are done, we can submit our script and it will be queued. The submitted job is shown on the screen and we can check the results afterwards with this ID. We have opened now the result files. We search for the found optimum scenario tables. Here we can see the different region IDs. The first region ID is, for example, calculate SAISO F90 at line 489 with the best frequency at 2.1 GHz. You can find this value on the table with an energy value of 2,552 joules. The next region would be Galerkin 3D Tetra file at line 193 with the frequency 2.5. In the next demo, we will show the tuning of the total cost of ownership. It is recommended to use it when there is need of balancing the influences of power-related costs and time-related costs. It is configured by setting the DVFS environment variable to 4. We also show the formula which is used in SuperMOOC, which considers the energy costs and amortized costs of the lifespan of the machine. We will use the same script that we use for the energy consumption metric. We simply change the environment variable to be equal to 4. This is equivalent to tuning for total cost of ownership. We recommend to change the file name of the output to TCO to easily recognize our tuning objective. The rest remains the same. We submit as usual our script and we have to wait until our job is completed. We can check the job if it is still running and check its progress with the tail command. Since the run takes several minutes, we will just check the output. We open the result files with the tail command. And we search, like in the previous case, for the optimum scenario tables. Found optimum scenario. You can see here the 3 different IDs, region IDs. For example, calculate SAISO F90, line 489. Frequency, the best frequency for TCO is 2.7. This is the 3rd scenario. And you can find the actual value on the 2nd table in the column for TCO. It is 1.66 cent. As another example, the 2nd region ID, the best frequency is 2.4 gigahertz. With a total cost of ownership of 22 cents. Finally, the 3rd region ID has a best optimum at 2.7 gigahertz with a cost of €1.42. We will analyze the results obtained. A lower frequency implies less energy per second. Since the execution time might be longer, the total energy consumption might nevertheless be higher than with a higher frequency. This is why the frequency obtained that minimizes the energy to solution was 2.1 GHz and not the highest 2.7 GHz. We have here 2 tables, one with the energy metric. Running with low frequency prolongates the execution, but leads to a significant energy reduction of 16%. And this is with respect to the highest energy consumption explored by the plugin. Performance degradation may be high in the case of energy consumption. For example, in one region, it was up to 25%. Therefore, it is recommended to check the total cost of ownership, which is shown on the 2nd table. In this case, savings of up to 10% of the total cost are possible, achieving a 12% of performance gain. This shows that the right choice of metric matters. Finally, we show an overview of the models and their corresponding tuning objectives. For more information, refer to the plugin user guides available on our websites.